This is Physics 102B homework on Chapter 18 for Porterville College. We're going to start with number 5. Number 5 has a negatively charged particle, so we're going to use the left-hand rule, moving horizontally in a region with a magnetic field directed vertically upward. For my diagrams in this video, I'm using map directions. So up on the page is north, down is south, which means that vertically upward would be out of the page, as you see drawn. So we're going to use the left-hand rule because it's a negatively charged particle. It's moving horizontally. Describe the particle's motion. So if you use the left-hand rule, you make it go horizontally. I've made it go to the east, although that's not necessary. And if the magnetic field is going up, you'll see, as I have it drawn, a northward force, and it's going to go around in a circle. So we can say for the answer that it's circular and horizontal. Number 8. Does the magnetic force ever do work on a moving charged particle? What you should remember, this goes back to Chapter 5, first semester, is that work is equal to force times displacement times the cosine of the angle between them. So here we have force and displacement. Now remember that the force that a magnetic field exerts on a charged particle is always going to be perpendicular to velocity. So if we have it displacing to the right, as I've drawn it, and force is up, that's a 90-degree angle, so work will always be 0. For number 15, a wire carries electric current horizontally from west to east, and here I have, using map directions, from west eastward. In what direction should a magnetic field point so that the force on the wire is vertically downward? So we'll use the right-hand rule. Point your right hand towards the right, towards the east, and make your thumb point into the page, and that would be downward. And your fingers should curl towards the southward direction. So south. Number 23. A negative particle, so left-hand rule, traveling northward, as you see it drawn with the blue line, drawn up, is deflected toward the east by a magnetic field. Alright, so you're going to use your left hand, point your hand in the northward direction. We're going to rotate our hand so the thumb points to the east, and the fingers curl into the page, which is downward. So down is the answer. Next, number 25. Number 25, a negative 50 microcoulomb charge. And so if we're looking for direction, we see it's negative. We're going to be using our left hand. Moves vertically upward, 75 meters per second. I've drawn this velocity vector coming out of the page with my north, south, east, west map directions. That would be coming upward. Which magnetic field will produce a northward magnetic force of 15 millinewtons? Alright, so we'll make our hand go up, in this case out of the page, make it rotate so our thumb points towards the north, and magnetic field, you should see, goes in the westward direction. So we have west. In order to find the magnetic field, we're going to use F equals QVB times sine theta. The angle theta between velocity and magnetic field is going to be 90 degrees, so given the multiple choices that there are. So we solve for B equals F over QV, and you should get 4 Tesla to the west. Next is number 35. Number 35. Magnetic field points north, as you see drawn in the picture. Find the magnitude and direction of the force on a charge moving westward, and we're going to do it for the same negative charge with the same velocity. Alright, so for part A, it's a positive charge moving westward. There's my velocity westward. Magnetic field north. We're going to use our right-hand rule for the positive charge. And you should get a force into the page, which is down. Force is QVB times sine 90 degrees. Once again, or sine of theta. Once again, theta is 90 degrees. So Q is 1.4 times 10 to the negative 6 coulombs times 1.5 meters per second. And here I've continued my expression over here. B 0.950 Teslas. So you multiply those together and you get 2 micronewtons downward. For part B, it's just a matter of changing to a negative charge, so you could say it's in the opposite direction, so it'll be 2 micronewtons upward, or you could actually use the left-hand rule. Either way, you should get an upward force. Number 37 has a variety of questions. A 1.5 Tesla magnetic field points northeast. So in all my different vectors, there's the northeast in the map directions. Find the magnitude and direction of the force on a 0.5 Coulomb charge that is moving 10 meters per second toward the northeast, southwest, and southwest. Okay, let's do part A. QVB sine 45 degrees, so we actually draw it. You can use the right-hand rule, and you're going to curl your fingers, and your thumb should point into the page. That's going to be downward. Q times V times B, and it's a sine of 45 degrees, so we get 5.3 newtons and down. For part B, on number 37, going to the east. Now, this is going to change things, particularly with the direction. If you use your right hand, point it along velocity, curl your fingers in such a way as to go in the direction of the magnetic field, and you should have your thumb pointing out of the page, which is now going to be up. And it's still 5.30 newtons. For part C, we draw the picture, and we have the magnetic field, same direction, but now C has it going to the south. And so we're going to use our right-hand rule, curl our fingers in the direction of the magnetic field. Thumb is still pointing up. It's now got F equals QVB times the sine of 135 degrees, 5.30 newtons up. For part D, it is going to the west. And so make your right hand go in that westward direction, curl your fingers towards in the direction of magnetic field, and you'll get it going, your thumb going down into the page. That would be downward. And finally, going to the southwest. Well, it's going opposite southeast, so you can just look at that and see it's not cutting across any magnetic field lines. It's going parallel, actually anti-parallel to the magnetic field, so you can see that it's 0. You can actually do the math and see that it's F equals QVB times the sine of 180 degrees, and that's going to be 0. Number 38. A negative 200 microcoulomb charge, so it's negative, moves downward. Find the magnetic field required to produce a northward magnetic force of 1.40 millinewtons. Use the right-hand rule, and you can see the magnetic field, use the left-hand rule on the negative charge, and see that the magnetic field goes eastward. We're going to use F equals QVB, but solve it for B. And we see we get 0.569 Tesla, and the direction is to the east. Number 41 has an electron, so we're going to use the left-hand rule. It's moving in the plus y direction, and there I have it moving upward through a uniform magnetic field in the negative x direction. Notice how the problem is stating the directions, x, y, x-axis, y-axis. So we're going to want to give our answer in those terms along which axis. What are the magnitude and direction of the force on the electron? Well, when you use the left-hand rule, your thumb points into the page. Now we can't just say into the page. We need to give it in x, y, z coordinates. With the standard x, y, where x goes to the right and y goes up, into the page is the negative z direction. So the direction negative z. Force equals QVB sine theta, and theta is 90 degrees. You should get 1.1 times 10 to the negative 13 newtons. The next part, part B, says find the electric field that would give zero net force on the electron. The electron is being forced right now into the page, or in the negative z direction. So we want something that will force it back into the positive z direction. Remember that electrons, or negative charges, go opposite the electric field. So I wrote down here, to force a negative charge in the positive z direction, E field should point in the negative z direction. So that's our direction that the E field should be. Let's quantify it. The electric field should be the force that we want to balance, which is what we found in part A. Now I took it to more digits for the calculation, so instead of just saying 1.1 times 10 to the negative 13, I've got 1.08936 times 10 to the negative 13, divided by the charge of the electron, the absolute value of that, and so we get 6.8 times 10 to the 5th newtons per coulomb. Next question, number 43. A proton in the positive y direction enters a uniform magnetic field in the positive z direction. So look at my diagram, and you see how I've got it. Velocity is in the positive y. The magnetic field coming out of the page, that's the positive z direction. Find the electric field that must be applied to give it zero net force. Well, first we use the right-hand rule to figure which way is the magnetic field forcing it. Use the right-hand rule and you find it is being forced to the right, which means we need an electric field that's going to go to the left. So E field must point in the negative x direction. Let's quantify it. Magnetic force should equal electric force. QVB equals QE, the charge divides out. And we're left with that the electric field is V times B. So 4,500 meters per second times 0.45 Teslas. So 2,025 newtons per coulomb should be the electric field. And that would be in the negative x direction. Number 46, a mass spectrometer used to separate uranium isotopes 235 and 238. What is the ratio of the radii of their circular paths. All right, so the ratio of the radii, I've got r of 238 over r of 235. Now we're going to use this equation here. This was derived in class and in the textbook, that in the mass spectrometer, the radius of any particle's path is going to be mass times electric field divided by the charge and the two magnetic fields. In class, sometimes I've used B and B prime, but I think the book uses B1 and B2, so those would be the two magnetic fields in the mass spectrometer. Now, we've got, let's plug this in. Here we have the ratios. So the mass, we don't have to worry about converting to kilograms. The actual units of mass are going to cancel out. So let's just use 238U, E, Q, B1, B2. And then we're going to divide by 235U, E, Q, B1, B2. You see most of those terms will divide out. And what we've got is the ratio of 1.013. Question B says singly ionized uranium ions pass first through 140 meter per second velocity selector and then into a 2.75 Tesla magnetic field. Find the diameters of the arcs traced out by the two isotopes. Starting with F equals ma, the force is QVB, ma is mv squared over r. We see 1 power of v divides out, and we're left with the radius is mv divided by qb. So the radius for the 238 nucleus, or ion rather, is 238u. We need to convert that because this is going to need MKS units, so multiply by the conversion of 1.661 times 10 to the negative 27 kilograms per U times 140 meters per second. Divide by the charge, divide by 2.75 Tesla, and we're left with 1.256 times 10 to the negative 4 meters. The diameter is going to be twice that, so 2.51 times 10 to the negative 4. Let's do that in millimeters, 0.251 millimeters. You do the same thing for the 235 ion, and it's going to be a diameter of 0.248 millimeters. It's got a tighter diameter, a smaller diameter, because of its slightly less mass. Number 59. Be aware, depending on the version of the book, I think that there's a wrong answer in the back of the book. I think it's this problem that had the wrong answer. Copper wire with a diameter given. Now, notice right away I've converted that to radius. That's what we're going to need. And a length of 10 centimeters. It is in a horizontal plane and carries a current of 2.15 amperes. Now, it doesn't state what direction, only that it's horizontal. Keep that in mind. I've drawn it, the current going east-west. Let's see. Find the magnitude and direction of the magnetic field needed to suspend the wire against gravity. Here's a force diagram, what I've done in the red, weight going down and the force on the wire going up. That will be, the force is going to be current times length times magnetic field. We're going to solve that for magnetic field. It's going to be mg over IL. Now, we don't directly know the mass, however, we're going to use density calculation. Since density is mass divided by volume, and we're going to be using the density of copper, we can say that its mass is the density of copper times the volume. I have changed out mass for density times volume. We don't directly know the volume. We're going to have to solve for that. We take it to be a cylinder, the wire as a cylinder, pi r squared times L. So density times pi times its radius squared times length times g, divided by current divided by length. And you see that length is going to divide out of that. So we have magnetic field is density times pi r squared g divided by current. We plug in those numbers, make sure we use MKS units all around, and we get 718 microteslas. Number 71. Electric motor has 1500 turn, 15 centimeter diameter circular coil on its armature. Find the magnetic field needed to produce a maximum torque of 25 Newton meters when the coil current is 12 amperes. Okay, the relevant equation is torque equals number of turns times area times current times magnetic field. We're solving for magnetic field, so let's do that. Tau over NAI. So tau, 25 Newton meters. We're going to divide by 1500 the number of turns. The problem says it's a 15 centimeter diameter circular coil. So its area is going to be pi r squared. So pi times 15 centimeters diameter means 7.5 centimeter radius. So that's why I have 0.075 meters. So there's pi r squared. Have the current of 12 amperes, and we get 78.6 milliteslas. Number 72. '72 says a long straight wire carries 2.5 amperes along the positive x-axis. Okay, so I've got the current going in the positive x-axis. Find the magnitude and direction of the magnetic field at A, a point 15 centimeters away on the positive y-axis, and B, a point 15 centimeters away on the negative y-axis. So positive y-axis, you can imagine the pen as I have it laid down right now is the y-axis. And it doesn't matter if it's over here, over here, over here, because it's not going to change. So I just have somewhere around here is where the positive y-axis is going to be. Negative y-axis is going to be down here. We're going to use the right-hand rule. Hold on. Find the magnitude and direction of the magnetic field. Okay. We're going to use the right-hand rule where we curl our hand around the wire as if we're grabbing the wire and our thumb points in the direction of current. And we see that above the wire our fingers come out of the page, and below the wires our fingers go into the page. So anywhere above the wire on that picture is going to be coming out of the page. So we'll say plus Z direction for part A. Anywhere below, and that this would be for part B, would be in the negative Z direction. To quantify this, we'll say that magnetic field off of a wire is mu naught, the permeability of free space, times the current, divided by 2 pi times your distance from the wire. Which, when you calculate those, whether you're doing part A or part B, it's 3.3 times 10 to the negative 6 Tesla, or we could say 3.3 millitesla. So part A is in the plus Z direction, part B in the negative Z direction. If we want to write this out in vector notation for part A, we could say 3.3 millitesla k hat, and part B negative 3.3 millitesla k hat. It just occurred to me that on a previous problem, I want to go back and look at number 59. It just occurred to me that the question asked, find the magnitude and direction, and I don't think I addressed the direction. Well, it doesn't say the direction the wire is going, except that it's in a horizontal plane. So let's assume that the current is going eastward. So we're going to face our right hand in the direction of the current, and we want an upward force, so we're going to turn our thumb upward and hand points, or fingers point in the northward direction. And I think that is the end. Yes, that is the end of the Chapter 18 homework solutions.